Welcome back to ECE 320A, your final homework assignment. This is the final lecture, meaning a lot of things involving final. Your final homework assignment is due tomorrow. It can be turned in today if you would like. Our last few sessions of office hours are listed there. Oh, and I haven't posted those on D2L, have I? So the people that show up to class know when I have office hours. I'll try to remember to post those, but obviously I will probably forget. Our review session is tomorrow. It will start at 4. It was about, I think, a vote of 27 to 19 or something, weighing the 4 to 5 and 5 to 6. We may still be going at 5 o'clock, maybe not. Maybe we will already be finished with the review, but I think there's plenty to keep us busy. The final exam is a week from today, 46 hours from now. I mean, what am I doing? I don't know. Two hours, I was thinking 48 for some reason and taking 2 hours off of that, but it's 2 hours earlier than what you normally come. So it's a week minus 2 hours is what I should have said, whatever that is. That will be our final exam. That's at 10:30 a.m. to 12:30 p.m. The process will be consistent with what we've done before. You'll have 4 sheets of notes, and those will be 8.5 inches by 11 inches in size, front and back. You can have a calculator, and now I'm really changing my practice, but there will be a practice final exam. It's already posted on the D2L site if you've been watching or looking. I haven't yet included any answers. I may just give you the answers and then force you to come see me if you have questions on how those answers are obtained. It's a multiple choice final in that particular semester. I haven't yet decided, but the number of problems will probably be consistent. There are 15 problems instead of maybe the 10 that we normally see in a 75-minute class exam. Also check D2L. I will try to post the notes and the video from tomorrow's review session in the same section, and that's basically at the very bottom of the content page on the D2L website. Today what I want to do is obviously finish up the class, which involves finishing up the filter example that we had started the last time we were here. I will discuss some concepts concerning two-port circuits, but according to the homework that was submitted, I think you were able to learn that on your own, and that's the whole idea, is at this point in this class, I think you can move on and start understanding two ports. If you look at the practice final exam, there's a Fourier series question on that, but you really don't need to know anything about Fourier series to answer it. You have the tools already available. Meaning if you can model a waveform by a sum of sinusoids, then if you know how sinusoids are processed through a system, which we do in the sinusoidal steady state based on their Bode plots, the system's Bode plot, you can figure out how the magnitude and the phase change for each of those frequency components. Question? Okay, I'll take it. I don't know that I can answer it. Question? The grades will be curved with all points included. So after the final exam, the grades will be curved. If that means, but that's how it was stated in the syllabus, I believe. So hopefully I'm not changing anything now versus what I had communicated. I think in the syllabus it says grades will be curved, so whatever that means. But that just means that I'm not being held to a 90, 80, 70 if I make the exam really, really difficult, which maybe I can't calibrate myself against what it needs to be. That allows me some wiggle room in adjusting. But I'm not also saying that only 5% of the students can get A's. If you all get in the 90%, for example, then I would have to give 50 students A's in 320. That would just break my heart. No, I would love to do that. Question? So I don't have a certain percentage that I'm targeting for assigning A's, B's, and C's. Does that make sense? Well, I can make the final exam, and you can actually be the one that makes it easy by doing a good job in studying. What's wrong with that? The final exam should allow you to now bring all of this material in, and it all starts to make sense in your mind or in your head, and you'll be prepared well for 340. And I think actually you guys can make the final exam easy, but look at the practice exam and see. That should give you a flavor. It will be comprehensive, the final. It won't emphasize necessarily the last piece, the two-port material, but a lot of this material is cumulative, meaning I could ask you one question at the end of the semester, topic-wise, and you could then use all of this material that you've used so far this semester or learned this semester to answer that one question. We were in goals. So I'll have a difficult in-class participation problem, which is really to sign your name on this piece of paper that's going around. Make sure if you're one of the first ones, if you can put the date and the class, and then start just putting your name on that. I don't want you to sign the TCE evaluation sheet, but I'll give you credit for filling it out this way, if that makes sense. So the TCEs, I'll leave class. I don't know how I'm going to tear this stuff down quickly, but I will put in my earplugs and put on blinders, and you can try to proceed with doing the TCEs as I'm finishing up here. I don't see that material until after the grades have been posted and submitted, and I want your feedback to see how we can improve upon ECE 320 the next time I teach it or someone else teaches the class. So I do look at that information, and it is used to evaluate me, actually, the TCE forms. Let's now start with where we said we were going to start, with an active low-pass filter. This is a third-order low-pass filter, and that was decided based on somebody saying, I wanted this much roll-off. If I said you have a third-order filter, how fast is your magnitude rolling off into the stop band? 60 dB. Where are you going in terms of phase at high frequencies? What phase angle are you approaching at high frequencies in a third order low pass? So if it's third order, you have 3 poles, and a low pass filter has all of the action in the denominator. There is nothing in the numerator. It's a constant. I mean, no zeros in the numerator, and so you have 3 more poles than you have zeros. 3 poles, each one of those poles gives you minus 90 degrees. 3 of those then give you minus 270, and you would be approaching minus 270. This particular circuit schematic is combining this generic second order section at the front and cascading that on the right-hand side with a first order section to give us our third order behavior. The denominator pieces associated with this set of R's, L's, and C's, we have the Butterworth pattern. We have a pole at -1, and then we have 2 other poles that are separated by that real axis by 60 degrees. And that gives us then our S² + S + 1 factor in the denominator. The right-hand side gives us an s plus 1 in the denominator, and all of those, if you looked at the overall transfer function of this circuit realization of a Butterworth low-pass filter, you would have now a bandwidth of 1 radian per second. The R's everywhere in this circuit are equal to 1. The C in the first order section is equal to 1 farad, and the C sub 1 and the C sub 2 are adjusted to give us the B sub 1 coefficient associated with the linear term in the S squared or in the quadratic equal to 1. I'm not sure if we got all of that put on the board last time, but that's basically where we made it to, I believe, at the end of our last lecture, and that's where I want to pick up at this point. Now, if somebody says, oh, I have a third order Butterworth low-pass filter, boom, you could immediately put this circuit down, but now if they say, oh, I want a different bandwidth than 1 radian per second, now you can scale these R's, L's, and C's. If I ask you a multiple choice question and I said, what is R equal to if you now have a bandwidth in this circuit of 200 hertz? What would R be equal to? The R over on the second order section. How do R's scale with frequency? They don't. It was a trick question, wasn't it? So it might have been none of the above for the answer. Is that making sense? So if I said scale this by such that the bandwidth is no longer 1 radian per second, but instead it's 200 hertz, you wouldn't have to adjust the R's, the resistors, because they are not frequency dependent. Obviously, the capacitors would have to be adjusted. Suppose now, so that was a third order low pass filter with a bandwidth of 1 radian per second. Suppose now we want a bandwidth of 200 hertz. Now we do need to scale. And what we need to scale is the frequency scaling, where K sub F, if you remember this K nu, whoops, that's not what I wanted. Let me say K sub F was equal to omega nu over omega old, or omega sub 2 is equal to K sub F omega sub 1. Or omega nu is K sub F times omega sub old. In this case, we had 2 pi times 200 for our omega nu, and we had 1 for our old. Our frequency scaling factor of K sub F is then going to be this 400 pi. Now, let's say that somebody adds the additional design constraint, and they say, suppose we also want the resistors to be 10 k ohms. Now we're playing with adjusting the magnitude scaling factor, K sub m, and that now we could say is R new over R old. In this case, we had 10K, and we had 1 for the original, or the old value. K sub m is now 10,000. Using those two scaling factors, we can now relabel, or really just change out these parameter values to be values that allow us to use 10 k ohm resistors and capacitors that will produce a bandwidth of 200 hertz, where now we have, let's say, R bar is now 10K, R1 bar, so my new variables will be barred. And what I had began with, all of my resistors were all 1, now they all become 10K. So wherever I had a resistor before in my third order low pass filter, I now can change those to be 10K. My C's are a little more involved. Now C1, that was in the second order section up top, that was a 2. I now need to divide that by both of these scaling factors. And doing that, I end up with 159.2 nanofarads. C sub 2, new value, becomes 1/2 over those scaling factors. We had a magnitude scaling of 10,000 and a frequency scaling of 400 pi, and this is now 39.8 nanofarads, which should be about 1/4 or is 1/4 of C1 bar, which it is. And then finally, in the first order section, we started with a capacitor value of 1, and the new value of that, when scaled by the frequency and magnitude scaling, becomes 7.96 times 10 to the minus 8 farads, or 79.6 nanofarads. Those now replace the R's and the C's in that third order realization that we just shown to give you a third order low pass filter with a bandwidth of 200 hertz and resistor values of 10K. Question? To K sub M. So K sub F. So now, K sub F, you just need to frequency scale, but typically we are going to have our original frequency set at 1 radian per second, and now I threw in maybe a slight curve and said we want our bandwidth in hertz. And that then forced us to say, oh, we need omega nu to be 2 pi times F nu, which F nu was the 200. Other questions on that example? So the 200 hertz is our break frequency, but now we've translated it, and if we were doing the Bode plots, we typically do our Bode plots in radians per second, and you would see that now, that minus 3 dB point at 400 pi, or about 1200 radians per second. But that now corresponds to 200 hertz. And you could rescale that in hertz. Other questions on that filter example? That now finishes that chapter, and now we can move into the last chapter in the book. Two-port circuits, which is chapter 18. There's a nice motivating example in the textbook, so you might want to read that. That occurs at the very front of chapter 18 and the last of chapter 18, and it shows you why you might be interested in two-port circuits. I was just on a thesis defense yesterday, and someone was dealing with antennas and electromagnetic thesis topic, and they deal with two-port network concepts. So this concept is used in many different ways. The way that, or one way of thinking of that would be to say, well, instead of worrying about this really complicated interconnection of circuit elements, can we just boil it down to where I have an input port and an output port and maybe a very quick or concise way of describing what's happening between those two ports instead of having 100 transistors and R's and C's in there? Can I boil it down? So if you have a complex design that you are dealing with, it might be easier to attack the design in pieces. And typically that's what we like to do as engineers. If we have this really big problem, and if you want to see some really big problems, you might want to go to Bear Down Gym today. That's where design day is occurring. The students that are a year ahead of you are now sweating out the judging competition and trying to demonstrate what they've been working a year to produce, which is their capstone project. And a lot of times those are broken down into pieces. Oh, here's my temperature sensor subsystem, or here's my pressure system. Here, and to explain this, maybe we have a system where we might have a photodetector over here. Let's just say that this is a photodetector. And I can't seem to spell, but you know how it's spelled. And we may actually need to amplify the information coming from that photodetector. We might then, after we've amplified the signal, we may want to get rid of some of the high frequency information, or it may not be information, it may just be noise. So how about we put a low pass filter to process that information? Now that it's a little cleaner, the signal is, maybe now we can boost it up with a power amp, and now that allows us to drive an actuator based on that photodetector's signaling information. And what we've done is, if you look at this, we have for each of these pieces, these are the pieces, this, we have an input side to that, that's a port, and we have an output port. And they have two terminals at each port. So here's the input port and the output port. The low-pass filter has an input port and an output port. The power amp has an input port and an output port. All of these now are what we can call two-port networks or circuits. Meaning maybe we can parameterize that low-pass filter instead of, now you know what a third-order low-pass filter might look like in terms of complexity. We just looked at it. Instead of worrying about all those op-amps and resistors and capacitors, we now parameterize it with 4 parameters. Maybe we say, oh, what are the H parameters of that low-pass filter? And let me just work with those 4 parameters instead of all of those R's, L's, R's and C's. In general, if we have 2 ports that we're playing with, let's now just give us some of the terminology or the constraints or the assumptions that we're making. Here is what we will call our 2-port. That should be consistent with our last picture, and maybe we'll just label it as S. With each port, we will associate a voltage across the 2 terminals. And we will also associate currents. And now the direction of these currents is important to how we've defined are parameters, two-port parameters that exist in that system or in that circuit. So I1 is going in, I2 is also going in from the positive V sub 2 terminal, and that's important to keep in mind when we're dealing with two ports. This is one of those two ports, and it's the input port. This is hopefully then clear as the output port. And a lot of times, instead of worrying what all's going on with S, if that's 6 op amps and a bunch of resistors and capacitors, just give me 4 parameters that describe that. So you may only be interested in some design processes. Maybe you are only interested in the terminal, and that doesn't mean final, that just means, sorry. This is the final lecture, right? So terminal, no, sorry. What is the behavior, or maybe we are only interested in the behavior at the ports. Here are some restrictions that we are going to agree to live by when dealing with two-port circuits. The first restriction that we will live by is we will say that there is no energy stored within the network. We're not going to allow somebody to put a bunch of batteries into that two-port. So we have no energy stored, let me say, within the network. So this is just one two-port that we're talking about, so I'll erase the S. The other, number 2, is we're not going to allow any independent sources within the network. However, that does not mean that we can't have dependent sources. So dependent sources are or will be allowed. The third restriction is that if we have current, let's say I1 going into the left or the input port, that same current I1 is coming out of that input port. So current into a port must equal the current out of the port. And sometimes that might be referred to as the port current requirement. Meaning, if we go back up here, what we're saying is that if we have I1 in, we have I1 out, and if we had I2 going in up above, we have I2 coming out down below. That's what that port current requirement is stating. Finally, let's just have 4 restrictions. All of these external connections that connect to the two ports, all external connections are made to either the input port or the output port. We're not going to be interconnecting inputs and outputs together. If you look at this two-port, how many variables have we identified? Yeah, don't count the I1s green and red as different or independent. Those are the same. we don't want to have initial energy stored in our system, but we can have inductors and capacitors in the two-port. But we don't want any charge or energy stored in the circuit to begin with. No energy stored within the network, but we can allow for inductors and capacitors to be in some elaborate circuit that we're now parameterizing by this two-port description. Question? No, we will be, so the question was, can we have op-amps? Yes, we can have op-amps. We can have active devices, and a lot of times you'll have op-amp circuits and you'll be dealing with H parameters. In this class, I think I only assigned Z parameters for the homework. That's all I want you to worry about now. But the book, I think, identifies 6 different sets of two-port parameters. You can have Z parameters, Y parameters, H parameters, G parameters, and then I think the book maybe uses A parameters and B parameters. Yesterday in the exam they were using S parameters, but that's what they use in electromagnetics. But if we count the different variables, we have 4 of those variables, I1, V1, I2, V2. Depending on the parameterization, we are going to have, those are the only 4 variables that we will be playing with. So we have 4 variables, but the different kinds of two-port parameter sets that you could have depend on which of those which of those 4 variables you pull out 2 and you say these are my independent variables. Those you play with or manipulate. The others would then be dependent. And depending on how you select the independent and the dependent variables, that will then produce these different kinds of two-port parameterizations. So we're going to have 4, we have 4 variables. We have 2 of those that we will consider to be independent. And if we have 2 independent variables and 4 variables total, we really just need 2 equations to find or create the interrelationships that are associated with that circuit. So we have 2 equations are needed to establish the interrelationships. Let's now look at some examples, and so that you're not completely bored with the definitions and terminology. Here is an example two-port. And this is a fairly basic, and it's actually, let's just say, it's a T network, and you probably won't be able to anticipate what that looks like structurally. So here we have so if you didn't have that bottom line, you could see that you now have a T shape where your interesting elements are now in the 3 pieces of your T. So let's say this is 1 ohm, here's 3 ohms, and this is 2 ohms. We can now identify or label the 4 variables of interest. We have our V1 and our V2 to be our input terminal and output port terminal voltages, and we have our currents, I1 and I sub 2, labeled according to how we've agreed to define our parameters. Let's now look at, for this particular T network, let's look at the Z parameters. And the Z parameters are called Z parameters because they do correspond to impedances. And if our parameters are impedances, then we need to multiply those impedances by currents to generate voltages. We're not going to change any rules here. So we're going to use Ohm's law. And because of that, our 2 equations that result with the Z parameters, we have a V1 equation is now Z11 I1 plus a Z12 I sub 2 and a v sub 2 is a z21 I sub 1 plus a z sub 2 I sub 2. Those are now our two equations that interrelate these four variables, and they interrelate those four variables by means of these z's, and those are our z parameters. The notation or the subscripts hopefully will be clear. The first row has ones as its first element, and then the second index in the z's corresponds to which current is being applied to that particular impedance. Now, if we want to try to find these z's for this T-network, we can start simply trying to analyze this circuit. For example, we could say, well, if I want to find z11 as a variable in that top equation, if somebody could fix I2 to be 0, and if I could now find V1 in terms of I1, I've found Z11. And that's really all we're going to do. Meaning if I set I sub 2 equal to 0, if I force that to happen, and I can do that by leaving the output port open, I sub 2 is 0. Now all I have to do is see if I apply I1, what do I get for V1? And now I have what Z11 is. Or you could write mesh equations. You could start writing these mesh equations. But now what you have to worry about is, in order to be consistent with the way that we've labeled these currents, you need to make those go in opposite directions. Usually when you do mesh analysis, I like you to write your mesh currents in a clockwise or counterclockwise, being consistent. Now you have one clockwise and one counterclockwise current, but you can now write KVL in terms of those. Let's now simply say that we've opened up the output port and we want to now find Z11. We will find that by setting I sub 2 equal to 0. If I sub 2 is 0, then we can simply say that, oh, V1 is simply 1 plus 2 times the quantity, or that quantity times I1. Or we could say I1 is V1 divided by 1 plus 2. It's however you like to see that. We could say, oh, I1 is V1 over 1 plus 2. And that now says that V1 is equal to 3 I1, or Z11 is equal to 3. Z11 was equal to V1 over I1 with I sub 2 set equal to 0, and that ends up being 3. That's one way of thinking of how to find Z11. Are there any questions on that? That's just doing Ohm's law or applying a KVL and setting I sub 2 equal to 0. Let's do the next one. Let's say we wanted to find Z12. Z12 in our governing equation would be obtainable if we could set I1 equal to 0 and still had I2 and V1. From this one, well, we'll say let's set I1 equal to 0. But if we now write KVL around this left mesh, we now can see we have minus V1 plus 1 times I1 plus 2 times I1 plus I2. This is now minus V1 plus 1 times I1 plus 2 times I1 plus I2 is equal to 0. But we just agreed to set I1 equal to 0. And in doing that, now we have 2I1 is equal to V1. I'm sorry, 2I2 is equal to V sub 1, or v1 over I sub 2 with I1 equal to 0 is equal to 2, and that is our z12 parameter. Questions on what I'm doing? Yes? So now in this particular, the question was, you can make this Z matrix and see that it's symmetric. In this all resistor network, that's true. But if we start having dependent sources, then don't expect Z to necessarily be symmetric, the Z matrix. But in this case, our Z matrix will be, if we call the Z parameters or put those into a matrix, it will be symmetric. Does that answer your question? So now if we look at Z21, in the governing equation, the second equation is where Z sub 21 lives. We can find that if we simply isolate on V2 and I1 and set I sub 2 equal to 0. Again, we can do a KVL equation. Now, though, let's look at the right mesh. And now we have minus V2 plus 3I sub 2 plus 2 times the sum of I1 plus I2. And that's equal to 0. Here we said, oh, let's let I sub 2 equal 0. And now we see then that Z21 is equal to 3, which is this V2 over, whoops, somebody is falling asleep. That should be 2. Actually, I was surfing the net. I don't know if you noticed that. Sorry, I can't do that and not get caught, right, on this. Never mind. So Z21 is 2, and we would expect that because somebody just asked the question, is your Z matrix symmetric? And Z12 then would need to be Z21 in this all resistor diagram. Finally, if we look at Z sub 22, we can find that by setting I1 equal to 0. We have our minus V2 plus 3 times I2 plus 2 times I1 plus I2 equals 0, but we're saying we don't want any current in I1, and now we see that Z22 is going to be V2 over I2 when I1 is equal to 0, and that's 5. And now we can see that this set of Z parameters can be looked at by saying V is equal to Zi, and the Z's are now, what was this? 3, 2, 2, and 5. Where 3 was what I1 touches as it's going through its mesh. 5 is what I2 touches, the sum of those resistors. And the 2's are what are common or shared between I1 and I2. Questions on that? Let's look at another example. Suppose somebody gives you the following circuit, and they give it to you as here's R1, here's R2, and let's put in a dependent source, and let's say that's beta V1. And we now can label these as V1, I1, I2 plus V sub 2. And now we want to find the Z parameters in this circuit. Meaning we need to find V1 and V2 equal to something times I1, I2. We need to find this impedance matrix. And looking at this, you could solve it many different ways, but maybe the most direct might be to say, oh, let me call that V sub A and that point V sub B, and let me just write KCL equations at those two nodes, just to get me some equations to write. I'm going to now write KCL at nodes A and B. If I do that for the leftmost node, or V sub A, I have I1 coming in. I have a current going down vertically, which is just V sub A over R1, and the current going to the right out of node V sub A is V sub A minus V sub B over R sub 2, and that equals 0. Or I could say the currents going in, which are I1, equal the currents going out, and one of the currents, the vertical current, was V sub A over R1, and the horizontal current going to the right there's one equation. And that was at node A. Node B, I can do the same thing. The current coming in is I sub 2 from the right, and now I have the current going down as beta V1, and the current going to the left is now VB minus VA over R sub 2. Oh, brother. Now I have V sub A and V sub B, and I don't want V sub A and V sub B, do I? I want V1, V2, I1, and I2. And then I want to write the V's in terms of the I's. But I can re-express the V sub A's and V sub B's in terms of I1s and V sub 1s and V sub 2s. Let's go back to our circuit. I want to now re-express V sub A and V sub B in terms of V1, I1, V2, I2. Well, VA is pretty easy, isn't it? That's just V1, as I have it defined, since there's no resistor between V1 and V sub A. So what I'm wanting to do is I need equations which contain these four variables, I1, I2, V1, and V2. Here are some observations. 1, V sub A is simply V sub 1. That was just by definition of the way I had labeled V sub A and the way that V1 is the input port voltage. V sub B I can relate to V sub 2 and I sub 2 pretty quickly. I can say that I sub 2, so the second observation is that I sub 2 is equal to V sub 2 minus V sub B over R sub 3. That's just the current going from the rightmost node towards V sub B. That's V sub 2 minus V sub B. That's the drop divided by R sub 3 gives us I sub 2. And now I need to rewrite that or solve for V sub B so that I can now get rid of V sub A and V sub B, or rewrite those in terms of the four variables of interest. And here, v sub b becomes v sub 2 plus, or I'm sorry, minus r sub 3 I sub 2. Now let's just plug those VAs and VBs in for the VA and VB in our original KCL equations, and we should end up with the following two new equations, which are just new in that they just contain I1, I2, V1, and V2. I1 now becomes V1 over R1. And the first equation had a V sub A, but that's just V1. Now it had a minus VB, but that's just V sub 2 minus R sub 3 I sub 2. And I divide that by R sub 2. That was V sub B. Now we can do the same process with our second equation, which was I sub 2. That's now beta V1. We didn't have to do anything different there, but now we replace V sub B again with V sub 2 minus R sub 3 I sub 2 minus V1, which is minus V sub A, and divide that by R sub 2. Now I have the two equations that I need. I can rearrange that. I can say, oh, I've got a bunch of I1s on the left and in terms of some V's on the right, or vice versa. But I should be able to now isolate the V1 and V2, meaning I can probably rewrite this as something times V1, V2 is equal to I1, I2. That's not what I want, or this could be some function of I1, and this could be some function of I2. If I can invert this quantity, whatever that is, then I can find my equation that I want. Does everybody understand what I'm doing? I can rewrite these two equations, let's say equation 1 and equation 2, where I have something times V1 plus something times V2 is equal to, well, that could even be, maybe I should do this a different way. This could be a function of I1 and I2. If you go through the algebra, I don't know if you heard that or not, but he was struggling with the algebra. You now end up with V1, V2 is equal to some Z11. And in general, if we are dealing with reactive pieces, these could all be functions of S. In this particular example, if you do that, you end up with your Z matrix being the following. And now this is another reason to use your napkin. Here's R1 over 1 plus beta R1. That's the Z11 piece. Z21 piece is R1 minus beta R1 R2 all over 1 plus beta R1. The Z12 piece is R1 over 1 plus beta R1. And now you can see that it's not symmetric. We had a dependent source in there in our circuit. And finally, the 2,2 entry is R1 plus R sub 2 plus R sub 3 plus beta R1 R2. No, R1 R3. Some of you have probably already done this. and you can check my work, over R2 times 1 plus beta R1. Those are now your Z parameters, and that's why I didn't go ahead and go through the algebra. It would have just been napkin intense. Okay? But that's what you could have expected, which now allows you to comment on or write that. If somebody now says, now what do I do? Well, you could either, wow, I'm about out of time. So let me do two things. So that's two ports. Suppose somebody gives you physical data that they've measured or collected from a circuit. So let's find two-port parameters from measured data. And again, we are going to look at Z parameters. And suppose somebody takes the following data. First, they open up port 2. And they say, with port 2 open, I measure V1 to be 8 millivolts. I1 is measured to be 4 microamps. And V sub 2 is measured as minus 8 volts. That's one collection of data. They open circuit the output ports, and they now measure these three variables. The next set of data is they short out or short circuit port 2. Under these conditions, V1 is now 5 volts. I1 is 5 milliamps, and I sub 2 is 250 milliamps. So you've now opened up the output port, taken some measurements. Now you've shorted the output port and taken some new measurements. And what you want to do is find the Z parameters based on these two sets of data points. With port 2 open, what do we know? We know now that the I2 current is 0, which allows us to find Z11. Z11 was V1 over I1 with I sub 2 equal to 0. And if we go through that, you'll end up with this being 2K. We can also find in the same first column the Z sub 2,1, which is V2 over I1 with I sub 2 equal to 0. And if you do that with the data that was collected, you get minus 2 times 10 to the 6th ohms. Now, with port 2 shorted, what does this give us? If I short port 2, does that tell me anything about the four variables? The voltage drop is 0, isn't it? So V sub 2 is equal to 0. Now, if V sub 2 is equal to 0, in our governing equation, we had V sub 2 is equal to Z21 I1 plus Z sub 2 I2. If we've set that equal to 0, and we just found this guy, and we now have collected under V2 equal to 0 conditions, we have a relationship or values for I1 and I2. That now allows us to solve for Z22, and Z22 now becomes minus Z21 over minus Z21 I1 over I sub 2, which ends up being 4 times 10 to the 4th, or 40K. And finally then, with V1 equaling Z11 I1 plus Z12 I2, we know Z11, we know V1, I1, and I2. Now we can solve for Z12. Z12 now becomes minus 20. And there are our Z parameters based on taking a couple of circuit conditions, opening up port 2 and shorting port 2, and now we can solve for the Z parameters under those conditions. One more thing. Let's say that somebody says, well, okay, so what if you have this set of Z parameters? I want to solve a problem. Well, you can now terminate that two-port network. Here is your two-port circuit, the input port and the output port. Suppose somebody now says, oh, hang a load on the output. So now you have some load out here. Maybe that's Z sub L. And they say, well, connect this to a source, which you could now model as a Thevenin equivalent. Here are the original terms of our two-port, and now we can analyze this for maybe the input impedance. Maybe we want to know, well, what does this source see at the input? Maybe they want the output impedance. What does the load see when it looks into that side? Or maybe you want the output current, or maybe you want the input current, or maybe you want the current gain, or maybe you want the voltage gain. All of those can be defined in terms of these relationships. Meaning, we already know what the two-port relationships are. We know V11 is Z11 I1 plus Z12 I2, and we know V2 is equal to Z21 I1 plus Z22 I sub 2. But by just looking at this interconnection structure, we can relate VG, ZG, and V1 and I1 and Z sub L to the output side. Meaning, we could say that over on the on the left side, we could say that V1, or if we went minus V1, now maybe we don't want to go minus V1. Let's go in the direction of I1. We could say minus VG plus Z sub G I1 plus V1 is equal to 0. That's one more relationship that we have. That's KVL at the left. We also know, if we just look at what's happening over here, we can define V2 and I2 in terms of Z sub L. We can also say, oh, V2 is equal to, now all we have to do is pay attention to the direction that I2 is going. It's now no longer consistent with the passive sign convention. Well, if we use the passive sign convention and say it's minus I sub 2 Z sub L. Now we have four equations that we can now solve for these various quantities using the Z parameters, the load impedance, Z sub L, the generator impedance, Z sub G, and the input or source voltage, V sub G. And that's now how this table of representations for a terminated two-port can be derived. And I will not do that, but what I will do is make sure that you have signed the attendance sheet for today. So that was a 25-minute discussion of Chapter 18. But you now have the skills to be able to acquire that information. Make sure that I collect those two sheets, and I would like to see or have somebody volunteer to do the TCEs, and I will